Greetings, and this is a problem of statics, two-dimensional statics concerning friction, and we're doing a classic wedge problem where we have a load that we are trying to raise by placing a horizontal force P onto a wedge that is at 8 degrees to the horizontal, and the load here is a large, in this case, aluminum block that is shoved against a wall of steel and a floor of steel. The wedge is of steel, and we are given the different coefficients of friction. So between steel and steel, it's 0.78, and between steel and aluminum, I'm just going to call it UA, is 0.61, and between aluminum and steel here again is 0.61. So the question again is, how much force P do we need to overcome the load and all the friction and so on before we can start lifting this load up? And secondary to that is, what's our mechanical advantage? Well, for starters, we need to understand what friction is, and our force of friction is equal to the coefficient of friction, mu, times the absolute value of the normal force. Sometimes I call this the most fun equation, F-U-N. It's actually the Greek letter mu. We use the absolute value because we find the direction is going to be opposite of the impending motion. And we'll use that several times in this problem. The opposite of the impending motion is the direction that we're going to need for the force of friction. And so the direction, maybe we're going to have a positive or negative direction of a normal force, that has no bearing on the direction of the force of friction. So we need to use something else. So we take its magnitude and then put in later the direction for the force of friction. Now in our case here, impending motion is defined as this block going up and this block going to the right. So we're going to redraw this as a system. We're going to take out the walls, and then we're going to have to replace those walls with forces, in this case red arrows. Force down, and our applied force here. And at each wall we have a normal force. We'll call this normal force at the wall, and here at the floor we have a normal force at the floor. And to go backwards, we have a force of friction. I'm just going to fill in mu s times the normal force of the floor. Now it's going this direction because we have decided that we're going to be pushing this wedge to the right. Now if we were trying to figure out how much force we need to apply so that the weight comes down, then we would have a frictional force that's going the opposite direction. But our block is going up, so that means our frictional force at the wall opposes that motion. So mu A times the normal force at the wall. So this is the free body diagram of the system. Note that for the system, we know the weight, but we don't know the normal force at the floor, the normal force at the wall, or P. And we've already used our equation of force of friction here, which helped us fill in frictional coefficients here and here, but we still end up with 1, 2, 3 unknowns. Now these two are multiplied by each other, so this is still the same unknown as this, and we'll combine those terms in the various equations that we end up with. But because I have 3 unknowns and only 2 equations, our summation of the forces in the x direction and summation of the forces in the y direction, I'm not even going to bother doing this system yet. I'm going to move on to the free body diagram of one of these 2 blocks. Now if you look at this block, we have an unknown force P and an unknown force N at the floor, and when I get it by itself, we also have frictional forces and normal forces going on right here in between the two. So I'm going to have 3 unknowns there as well. But if you look at this block, we have a known weight and just 1 unknown here, the normal force at the wall. And there's going to be the normal force at the interface here. And those are going to be my 2 unknowns. And that's why I'm going to do free body diagram of the block next.
All right, so we have our block and a force down, the weight of the block, and we have a normal force coming in from the wall, and we have the frictional force at the wall as shown before, and we have here some frictional forces at the interface. So we have a normal force at the interface, and now the block seems to be traveling up the wedge. So therefore we have a frictional force that's traveling down the wedge. So now this is the block is still aluminum and the wedge is still steel, so we're going to use mu A here. Okay, so here's our free body diagram of the block. And we will take these forces and put them together in just a concurrent force diagram. Although they're not really concurrent forces, they still all have to add up to 0. So we got our weight, frictional force at the wall, our normal force from the wall, and and there's mu A N I. Now the weight is going straight down, the normal force at the wall is going to the left, so we have to work on the angles with these two. So if this is our horizontal, we have right here minus 8 degrees, and right here 90 degrees to that is 82 degrees. So now I'm going to sum the forces in the x direction. And they better be 0. And looking at my diagram here, this is obviously horizontal. This has a horizontal component to it, and so does this. These two, they're vertical, so we don't have to worry about them. NW is at 180 degrees. So we take the cosine of 180 degrees plus Ni times the cosine of 82 degrees plus mu A Ni times the cosine of negative 8 degrees. Well, we know mu A. We can clearly calculate cosine of 180, cosine of 82, and cosine of negative 8. So we get 0 equals, cosine of 180 is simply minus 1, so it's negative NW, and cosine of 82 degrees is 0.139. Multiply that by Ni. And we add that to mu A times the cosine of negative 8 is 0.604, and that's also times Ni. Now we combine these terms, and we get 0 equals negative NW plus 0.743 Ni, and just put NW on the other side. NW equals 0.743 Ni. Well, that doesn't do us a whole lot of good because we still have one equation with two unknowns, but that's okay. We have another equation, and that is going to sum forces in the y direction. They must equal 0. And we've got everybody involved here except the horizontal normal force at the wall. So we'll have a few more terms this time around. So we have Ni sine of 82 degrees plus mu A Ni sine of negative 8 degrees, and these two forces are both downward, so I'm going to subtract them, minus mu A and W minus the weight W, and that's given to us as 180 pounds. Okay, well, here we have, again, one equation with two unknowns, Ni and Nw. We're going to simplify this and then put this expression into here. So 0 equals the sine of 82 degrees is 0.99 multiply that times Ni plus 0.61 times negative 0.139 Ni minus 0.61 NW minus 180 pounds. Okay, so I'm going to take this, multiply it by Ni, this, multiply it by Ni. I'm going to combine these terms. So 0 equals 0.905 Ni minus 0.61 NW minus 180 pounds. Okay, now we can take this cool thing and plug it in up here as 0 equals 0.905 Ni minus 0.61 NW down here is 0.743 Ni. I'll just show you that. Minus 180 pounds. So now you see that we've got one unknown. Just Ni here and Ni here. We just need to multiply things out, combine terms, simplify everything, and we're almost home for that. So I combine them and I get 0 equals 1.358 Ni minus 180 pounds. Put 180 pounds on the other side. Zero equals 0.452 Ni minus 180 pounds. So all we had to do is put 180 pounds on the other side and divide through by 0.452, and we get Ni equals 398.4 pounds. Okay, that was for the free body diagram of the block. But now we have the normal force that is exerted on the wedge. So when we go to the wedge, it will only have two unknowns, P and the normal force at the floor. I'm going to write our conclusion for Ni down at the bottom here, and then erase so we can get a little more space for our wedge. Okay, so we have wedge looks like this, and we have the applied force P, which should be horizontal. Then we have the frictional force going back at us. And remember, this is the steel interface, so we have mu S and F. Then the normal force of the floor. And then now we're switching free body diagrams from the block to the wedge, and these are internal forces, so we switch directions. So we've got NI coming downward, so it's going to be 82 plus 180 degrees. And the frictional force, mu A NI, right there. I'm going to redraw these forces here so you can look at them a little easier to do our equation. So here's our P. Might be a little bit tougher to make our angles here, but with respect to the positive x-axis, our frictional force at the interface is 8 degrees less than 180, so it's 172 degrees. And our normal force at the interface is 8 degrees less than 270, so it's 262 degrees. So we will attack this once again using our forces. So if I do sum the forces in the x direction, they have to equal 0, so we have a lot of forces here. We've got mu s nf going in the opposite direction as p, so we're going to make minus, again that's the frictional force of the floor, plus p plus ni cosine of 262 degrees plus the frictional force at the interface times the cosine of 172 degrees. Okay, so that's all ready to go. 0. And that mu s is 0.78. And we still don't know NF, so we'll keep that as a variable. P is still what we're trying to find. 262 degrees is negative 0.139. Multiply that by Ni. Now we've got 0.61 times the cosine of 172 is negative 0.990 Ni. Guess what? We have Ni. Ni is 398.4 pounds. So we can eliminate this as an unknown and this as an unknown and leave us with NF and P. If I combine these terms together, it's negative 0.743 Ni, and Ni is 398 pounds. And we can solve for either NF or P. In this situation, I'll just solve it for P. So P equals, so bring P over the other side, multiply everything through by a minus sign. 0.78 NF, and this evaluates out to 296 pounds. So again, we've got two unknowns in our equation, but we've got one more equation to go. Sum the forces in the y direction. They have to equal 0. And our forces in the y direction. Don't have to worry about the horizontal ones, P and mu s and F. So we just have mu A Ni times the sine of 172 degrees plus NF. That's totally vertical, so we don't have to worry about its angle, plus Ni sine of 262 degrees. We've got mu A, we have Ni, we have Ni here, so we just need to solve for NF. So bring NF over here. And since we brought NF over here, we had to multiply through by a minus sign. 0.61. The sine of 172 degrees is negative 0.139. You got to multiply that. And then the sine of 262 degrees is negative 0.990. You'll notice a pattern with a lot of these same sines and cosines at these angles. It's to be expected. And again, Ni is 398 pounds. So we evaluate all that out. NF equals negative 398 pounds times negative 0.905, and NF equals 361 pounds. Great. Now I've got that. I will take this value for NF and plug it in up here. And I multiply 0.78 times 361, add it to 296 pounds, and my force P is 577 pounds. Last but not least, we need to check that against the system here. Take my forces in the x direction, have to equal 0. I have P plus mu s and F, the frictional force at the floor. And this should be negative. And we'll also subtract normal force at the wall. And we take 0 equals 577 pounds minus 0.78 times 361 pounds minus NW, which is 0.743 times NI. So let's go back and do that. 0.743 times NI, which is 398 pounds, is negative 296 pounds. So okay, if I evaluate this whole expression, we come up to approximately 0. So that checks out. Next, we sum the forces in the y direction. Possible we could have made a mistake in one direction, not both. And we have the weight coming down, minus 180 pounds. Add to that the normal force at the floor going up, and subtract from that the frictional force at the wall. Zero equals 180 pounds plus the normal force from the floor. We found that to be 361 pounds. And subtract 0.61 times 296. And that comes up to be approximately 0 pounds as well. And we've checked our work this way. In summary, we have a fairly complicated problem with a wedge that's supposed to be pushing in towards a wall, lifting up a fairly heavy object. The wedge has an angle of 8 degrees, and we have different coefficients of friction at different surfaces, and we had to look that up. What we would hope in a situation like this is that the force to push it in is less than the force that it is driving up, so that we have a mechanical advantage greater than 1. Remember, mechanical advantage, in this case we'd be looking for the force out over the force in, and the force we're getting out is we're lifting up this block. This block is 180 pounds, and the force we're putting in is P, and P ends up being 577 pounds. So our mechanical advantage isn't very advantageous. It's less than 1. In fact, it's only 0.31. Well, what's the point? The point here is threefold. Number one, you may not have the ability to apply a force vertically, but you might have the ability to apply a force horizontally. For example, if you are moving furniture, it's pretty easy to sit against a wall and use your legs, the strongest part of your body, to push that weight across the floor. Yeah, you could use a crane, but it would be kind of difficult to get that into your house. So that might be part of the reason that one might choose this method of lifting. Another reason is that this situation is self-locking. In other words, you might push it in, but because of the angle, is the weight going to just come down and slide it right back out? You want to make sure that if you want to keep it in position, that that's not going to happen, that the friction available is going to keep it in place. Third point is to show the importance of lubrication or other material surfaces. These coefficients of friction are fairly high and could really make it locking, but also make it very difficult to move. So you need to have an appropriate balance of that. Well, once we had this set up to get out some form of mechanical advantage or some design that we were hoping to achieve, to analyze it, we looked at the system and looked at all the different forces on the system, realized that we didn't have enough to solve it from that. We chose the free body diagram of the block because we had two equations and two unknowns. We solved for them. We had to create some new forces at the interface, and then we took those forces at the interface and applied them to the wedge, switching signs because we switched free body diagrams for an internal force. Then we did the exact same thing, solved two equations for two unknowns, made sure we kept our angles correct, and eventually substituted back in to find our applied force. And of course, just as important as everything else, we checked our work. Again, I hope this helps.